Okay. So let's go ahead and start. So I believe I'm already sharing the warm-up, yeah? Item number 1, draw a free body diagram for a wheel rolling down a ramp. And then item number 2, draw a free body diagram for an object falling at terminal velocity. So just a quick review about the phrase terminal velocity. I think I've only used it like twice this whole class. Does anybody want to talk about terminal velocity? What does that mean? So terminal velocity, all that means is that when an object is falling on Earth, it's going to accelerate according to the acceleration due to gravity, which we've talked about a bunch, right? 9.81 meters per second squared. But because we live on a planet with an atmosphere, the faster and faster and faster and faster you fall, the more and more and more air you are pushing through at any given second. So if you fall far enough, you fall so fast that air resistance becomes so great that it will stop you from falling any faster. All that terminal velocity means is that it is falling at a constant velocity, a constant maximum velocity. And there is enough information to draw the free body diagram there. Yeah, take about 60 seconds and then we'll go over this. That should be all it takes. And then today we'll do a review of projectile motion. And then for tonight's homework, I'm just going to assign one of the videos from the review channel for y'all to watch. And then tonight I'm gonna go over your guys' submissions for that most recent practice free response. And then tomorrow we'll go over the answer to that in class. Does that make sense?
Yep.
Okay. Okay. So item number 1, I have a wheel rolling down a ramp. Picture looks like this, and I only put this here just to remind us of the, the physical situation. And I'm going to also put an or here because there are two completely disparate, I mean, not completely, but there are two slightly different free body diagrams that I can give that are both going to be valid here. And all I'm going to do is I'm going to put an X, Y, oh, I'm getting a notification that says I'm laggy. I'm going to wait a second.
It says network bandwidth is low.
Yeah, that's on my end. I'm going to put two different versions of the free body diagram over here, just to show that there are two correct answers that would both be given full credit on the AP test. And I just want to do more of these free body diagrams, just because, no offense, we all get a lot of them wrong still, even though it's super late in the year. And it's not just y'all, man. People have a hard time thinking about free body diagrams. I still see undergrads who are like 22, 23, who make the same types of mistakes. So what forces would be acting on a wheel as it rolls down a ramp?
mg sine theta.
So I'm going to go with, for my first version here, just mg. So yes, the wheel has a weight due to gravity on Earth, right? And that's what's pulling it down the ramp. So first off, I'm going to put on here a downwards arrow, and that's going to be mg. Keep in mind, when we draw free body diagrams, we are using vectors, which means all of them should originate at the origin. The origin is meant to represent the center of mass of the object. And the lengths of the vectors are relevant because the longer a vector, the bigger it is. So if you have one force which is bigger than another, it better be represented by a longer arrow. What else is acting on it aside from its own weight?
Normal force.
Normal force.
It is on a ramp, and all objects in contact with each other have some associated contact force. We normally call it the normal force because mathematically speaking, normal means 90 degrees, perfectly 90 degrees, the way the pen and this ruler are. And so the normal force needs to come out of the ramp, whatever angle it's at, 90 degrees to it. So we're also going to have a normal force acting on here, And that normal force must be, by definition, equal to or smaller than the weight. So whatever your normal force vector is, it has to be shorter than mg. What else is here? There's one other force.
Is it mg cosine acting from the ball on the ramp?
Nope. I will talk about trigonometry here in my second solution. What causes a wheel to roll at all?
Is it friction?
That's the key. Whenever an object rolls, there must be friction there. That's what makes it roll. The fact that, like, when you're riding your bike, the thing that is actually causing the wheel to rotate is the fact that it is rubbing against the ground. And the friction between the rubber surface on the wheel and the asphalt itself, that grip, is what causes the wheel to stay in place and rotate about its axle as the frame moves forward. If there was no friction, if you tried to ride a bicycle on an ice rink, for example, the wheels wouldn't turn. The wheels would stay in place as they just glided over the surface. So whenever there is rolling, there has to be some small amount of friction, which I'm going to call in this case F sub mu. And that tiny amount of friction, however friction is oriented, keep in mind it always acts opposite to the motion. So if we're rolling down the ramp, then the friction must be up the ramp. And this is going to answer the questions for those of y'all who were talking about sines and cosines. Doing the trig does not affect the normal force, its magnitude, or its direction. It does not affect the frictional force, its magnitude, or its direction. Those are identical. If you are going to trig this up, here's what happens. It splits the weight. So if you had mg on here and you also had mg sine theta and mg cosine theta, that is all technically wrong. You are doubling one of the forces. If you break this up, this mg, we can have an mg cosine part into the ramp. We have an mg sine part down the ramp. But it is important to realize that if you were to take mg cosine theta and add it up with mg sine theta, that would give us back exactly mg. Nothing more, nothing less. And just a real quick review of this for those of y'all who had pre-cal last year and might have forgotten all of our identities. Here's the deal. Here's what's up. Mg cosine theta, mg sine theta. My argument is they must always add up to mg. What's the angle between mg sine theta and mg cosine theta? What's this angle between the cosine part and the sine part?
90.
Yeah, and what's the rule about adding two things that are 90 degrees to each other? What theorem do we use when we add up two things that are perpendicular? What's 3 plus 4?
7. Oh, Pythagorean theorem.
If I have 3 plus 4,
Oh my god.
I have 3 and I have 4, and I add them up, if they're end on end, then that's just 7.
Like 5 minutes ago, but instead I
Mute your mic.
woke up 4 hours ago.
Cedric?
It's okay. I'm trying to wake up earlier too. It's good.
Yeah, but you're not doing it by wanting to.
I am doing it, but
Hey, Cedric?
Yeah.
Tell Ethan I said hi.
I literally have my microphone up.
Lol. Hey, anyway, I have 3 and I have 4. If I add them end on end, that gives us 7, right? But if I have 3 and 4 and they're 90 degrees to each other, what's 3 plus 4?
7.
Not if they're 90 degrees to
5.
each other.
Oh, sorry, 5.
Then it's 5, because we're talking about the hypotenusal length here. So the same is true down here. So here's the argument. Mg cosine theta, mg sine theta, they're 90 degrees to each other. So if I want to add them up, it's actually mg cosine theta squared plus mg sine theta squared will give us whatever our sum is, which I'll just call that h squared, right? The sum of these two things, so long as they're 90 degrees to each other. This is going to give me mg squared cosine squared theta plus mg squared sine squared theta is equal to h squared. I'm going to factor out mg squared, so it's mg squared times sine squared theta plus cosine squared theta is equal to h squared. And pre-cal people, what is sine squared plus cosine squared by definition?
1.
1.
This is always 1. And so mg squared is equal to that hypotenuse squared. And so if you take mg cosine theta and mg sine theta and add them together, it's just mg. So keep in mind, whenever you are splitting up some vector using trig, do not double list it, because you're basically saying that it is present twice. You should never draw this. You are either writing out the components or writing out their sum, but not both. Is this okay?
Yep.
Okay. Item number 2. An object is falling at its terminal velocity, which is to say you drop an object and you let it fall up to its maximum possible falling speed until it is retarded by the atmosphere. When you're falling without a parachute, a human's terminal velocity is about 250 meters per second, which is really close to the speed of sound. Speed of sound is 330, but the moment you yoink that parachute, it drops your terminal velocity way down to about 3 or 4 meters per second, so that when you impact the ground, you don't just die, right? And so oddly enough, even though it doesn't seem the same, the free body diagram for a person falling at their terminal velocity down at 250 meters per second, and the free body diagram for that same person once they pull their parachute ripcord and they deploy their parachute, did you know that the free body diagram for these two scenarios is exactly the same? It has to be because of what the definition of terminal velocity is. If you fall at 250 meters a second, if you fall at 4 meters per second, the free body diagram is identical. And I think this is a really good example to get at why it's so hard to think about these things. Free body diagrams are not showing us motion, they are showing us forces. So I'm going to go ahead and I'm going to put down my person, and what forces are here?
mg down.
That's the free one. If you are falling, it's because you are on a planet with gravity, so there must be some mg. What other forces here, and how do we know?
There are air resistance.
There is air resistance, and how much air resistance is there?
Less than mg.
Is it mu?
Is it what?
Mu?
So you could call air resistance a type of friction, so to call it some F sub mu would be fine in terms of lettering. But what my question is to y'all is, how much air resistance is there and how do you know?
Isn't it less than mg because like you're still falling down?
Nope.
Oh.
Terminal velocity is a constant maximum velocity. If velocity is constant, what does that tell us about acceleration?
0.
So constant v means acceleration is 0, and according to Newton's second law, what does that tell us about the sum of the forces?
0.
Therefore, if the sum of the forces is equal to ma, and mass times 0 tells us the sum of the forces is 0, therefore the sum of the forces has to also be 0. This is not adding up to 0 right now. So how much air resistance is there?
9.81 meters per second squared. Like
That's how much acceleration of air resistance you are getting, but
like the same force as like the mg.
correct. As you are falling, the faster you fall, the more and more air resistance there is on you. So at the start, the air resistance vector is very small. But the faster you fall, the bigger and bigger and bigger and bigger and bigger that air resistance vector gets. And once it is equal to the weight vector, you stop accelerating. So that is to say that the force due to friction is equal to negative mg. And there should be no other forces here. Those are the only two acting on an object that is freely falling through an atmosphere. And like I said, this free body diagram is appropriate for both a person without a parachute falling at some great speed and a person with a parachute falling at a small speed, because information about velocity is not present on a free body diagram. If you are drawing a free body diagram and you put an arrow on there and you're like, this is the velocity, you are making a huge mistake. Are there any questions on this free body diagram warm-up?
No.
Okay. So let's go ahead and get into our quick and janky review on projectile motion. And it's just going to be, like I said, quick, dirty reminder of what the rules are, how we want to think about it. So projectile motion isn't actually a topic of physics. I mean, it's a useful thing. And in terms of like the historical development of physics, it was of great interest because when Newton was developing his mechanics, right, a mathematical way to do a mechanics, we were also still doing warfare, largely with melee weapons. And at the time, we were developing fairly early cannons, right? And back then, if you wanted to fire a cannon or aim a cannon, you just got good at it the same way you like get good at throwing and catching a baseball. Like when you catch and throw a baseball, right? You're not doing physics in your head. You just kind of get a feel for it by doing a lot of practice. But when it came to projectile motion of larger weapons, as soon as people realized that, hey, you can actually use math to predict what's going to happen, the way that objects are going to move around through the air, one of the earliest applications was calculating how far a cannon goes based on its known angle and its known firing velocity. And people came up with tables that would just let you look up the angle of like, hey, we're trying to shell people who are 500 meters away from here. What angles do we set the cannon at? Look it up in your table of pre-calculated values, set the cannon to that angle, and now you're raining shrapnel on the French or whoever it is you're killing. I only say the French because Newton was English, and you know, they've been at war for hundreds of years. Like them being cool is a post-World War II development. Nonetheless, here's what's up with the actual topic. And does anybody know what is the actual topic of physics that we're doing when we talk about projectile motion? We're still actually talking about kinematics. But yesterday when we talked about kinematics, all of those kinematics questions that we were doing were occurring along a single dimension of motion. Projectile motion is actually the topic 2D kinematics. And here are the big takeaways that we want to take away from 2D kinematics. Independent dimensions. And whenever you see the phrase independent dimensions, when you are talking about science or math, means perpendicular. And the reason why we say that perpendicular dimensions are independent of each other is that if I had basic graph paper set up, some X, Y, Z, where this is 1, 2, and 3 in the Y direction, 1, 2, and 3 in the X direction, it's pretty straightforward that, okay, if these are perpendicular and I go increasing in the X direction and I increase X from 1 to 2, does that change my Y value?
No.
No.
No. If I increase X, if I add 1 to my X direction, I go from the point 1, 1 to the point 2, 1, but Y is unaffected. Y is still 1. Same is true if I add Y's. So if I'm here and I add 1 to my Y direction, I go up to here, but X is still 2. I go from 2, 1 to 2, 2. So the reason why we say that independent dimensions, which is just to say perpendicular dimensions, is the simple fact that motion in one of them, changing values along that line, it just can't change values along another line. Now, there is a much fancier way to prove this using calculus, but that's way outside the scope of this class. You will see that proof in college physics. Nonetheless, independent dimensions of motion are mathematically independent. That's why when we do our mathematical treatment of these things, We solve the x and y problems as if they don't affect one another. Independent dimensions of motion are mathematically independent, except for the fact that they are both parametric equations of time. You get one equation of motion in the x direction, you get another equation of motion in the y direction, and both of those are a parametric that describes the overall pathway. Back from pre-cal, do y'all remember parametrics?
No.
Here's all that parametrics is talking about, and we could do a much deeper dive on this, and if you want to know more about parametrics, I'd recommend pulling up a video and watching an overview of it, but here is the quick ghetto version of this. If I fire a projectile, what path does it make through the air?
Parabola.
It makes a parabola, and this parabola has a name. This is called our trajectory. Just because this is so studied that we have our own sets of vocab for it, and the point at the top would be the apex of our trajectory, and we have all this other language to describe it. But what we're doing mathematically when we solve this system to figure out its range or its maximum height or the amount of time that it takes for all of this to happen, right? Tick, 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 the time of flight, is you are actually getting two equations. We are saying we have one equation of motion that goes up and down, that is our y of t. We have another equation of motion in the x direction, that is our x of t, right? So instead of having one regular old parabola, we have one equation talking about y and another equation talking about x. And in fact, what parametrics tells us is that if you were to take the x equation and solve it for time, then take that equation and plug it into the y equation and get rid of that time value, you would be able to show that by substitution, y would be proportional to some kind of function of x squareds. You would be able to show mathematically that if you take time, solve for it, and substitute that into your y value, that y is definitely this parabola. The only thing that makes a normal parabola different from a parametric parabola is on top of the part where we have that y is equal to ax squared plus bx plus c, and then we could do all the fancy parabola math. The only other thing that makes it a parametric is the fact that each one of these points is associated with a time. So we could say that this is where we're at time 1, this is where we're at time 2, we hit the apex at time 3, over here we start falling at some time 4, some time 5, we're closer to the ground, and then we impact the ground at time is equal to time 6. That is all that parametrics means, that on top of each one of these points having an x and a y position, they also have a time coordinate. Is this okay?
Yeah.
Okay. Big ideas, and this is just a big idea that makes it easy to see the way in which we are decomposing stuff, and then we'll show the time decomposition part as well. Let's go ahead and take a quick reminder of a thing that when I say it, it'll hit you like a ton of bricks, but I guarantee you haven't thought about it in 4 months, and you definitely haven't thought about it in the last month because of all of the COVID stuff going on. But who remembers back when we were all young and naive, the bullet drop?
Yeah.
So what is the bullet drop experiment? Talk me through it.
Didn't it it was like the bullet and they shot it at like a certain angle and they compared it to something else, right? And it went the same distance.
We have some of the right terms in there. So we're definitely shooting it at an angle, and what the angle is crucial. The angle is 0. So
Okay.
for the bullet drop experiment to work, the bullet which is being fired has to be fired parallel to the ground. And what are we comparing it to?
Oh, was it another bullet with a different angle?
Another bullet which is not a different angle, another bullet which is just being dropped.
Oh, okay.
So we fire one projectile to the side at an angle of 0, and at the same time we drop one projectile straight down. I'm about to share my screen, which I don't know how fair use works, but I assume if I say fair use enough times, it counts. So fair use, fair use, fair use, fair use. This video is from Harvard. So what we're looking at here is this guy gets paid more money than I do to set up these labs and lab demonstrations because he's got that sweet, sweet Harvard endowment money. And he is setting up a device which is literally designed to do a perfect bullet drop every time. It's a spring-loaded shooter. He's making sure that it's level, it's perfectly parallel to the ground so that it, works properly. And it's using mechanisms to make sure that both of the balls are fired simultaneously. To the left, there's a rod where we're going to place one cord out pull ball, and it makes it so that when the spring-loaded launcher launches, it drops straight down because the pin is being pulled out of it. And on the other side, we have a regular pool ball that is being smacked. And because it's a single mechanism doing all of the motion, it guarantees that one ball is dropped at the exact same time that the other ball is launched out to the side, or launched out sideways. Now, both of these balls travel different distances. They also travel at different velocities. Those things are not the same about these two flights. However, the ball on the left falls straight down, the ball on the right is launched out, but notice there is something that is the same about both of their trajectories. They both impact the ground simultaneously. One more time. Simultaneously. 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 Okay, great. Is that okay?
Yeah.
And so here's what that tells us. And here's how we want to think about this and these parametrics. I have ball 1. I have ball 2. Both of these are being dropped from an identical height, except ball 2 has some velocity. Some V0, which is not equal to 0, whereas ball 1 has a V0, which is precisely equal to 0. Now keep in mind, these results are not the same unless this guy is parallel to the ground, which is to say its angle of launch theta is also going to be equal to 0 degrees, because what would happen if I shot it up? Would it hit the ground at the same time, earlier, or later?
Later.
Later. That will delay the amount of time that it takes to get to the ground. Or if it had a negative angle, if it was shot towards the ground, would it hit the ground sooner, later, or at the same time?
Sooner.
If you shot it at the ground, it would actually beat ball 1 to the ground. But under these conditions, both of these balls fall to the ground at the exact same time. And here's why. This equation of motion for the two balls is the same, what they're doing up and down. So let's build a y of t. And to build this y of t, I'm going to use kinematic equation 2. So it's going to be equal to 1/2 gt squared plus v sub o t plus y sub o. What is their initial velocity in the y direction? What is this guy's initial velocity in the y direction? Before zero, because before we drop it, it's not falling yet. And this guy, what's his initial velocity in the y direction?
0.
Also 0. His initial velocity is in the x direction because it's going to be shot out to the right, but his initial velocity up and down is also 0. So for both of these, this here, well, that's 0. And what is their initial y position? If I call this 0, then how high are they above that?
H.
H. So for both of these balls, y as a function of time is going to be equal to 1/2 gravity time squared plus h. This is true for both of them, so I'm not going to label which y this is. This is their y equation. And then number 2, I want to know, well, what are their x equations of motion? So for that, I'm also going to use kinematic equation number 2. So their x of t is going to be equal to 1/2 at squared plus their initial velocity in the x direction times time plus x sub o. Now, for the sake of simplicity, we're just going to say that both of these start at an x position of 0. So this guy is 0. They just both start all the way to the left. However, what is their acceleration in the x direction? How much acceleration acts on these guys left and right?
0.
So for the x equation of motion, this is 0 because there is no acceleration that way. So x of t is going to be equal to just whatever their initial velocity was times time. And so each one of them is going to have their own independent x equation of motion. So x of ball 1, we said his initial velocity was 0. So x1 of t is just 0, and it doesn't change over time. That's the same as saying, well, if this guy doesn't have a velocity left and right, its x position doesn't change. It's not going to go left. It's not going to go right. It's just going to fall straight down. So for ball 1, this is a complete equation of motion. Now for ball number 2, x2 of t, that's going to be equal to its initial velocity, because I don't know what this velocity is, but all that matters is that it's not 0. And so ball 2 is going to have an equation of motion, v sub ot. And if you want to know, well, hey, what does this ball do? That is going to be some kind of combination of equation 1 and equation 2. We need to combine its x equation and its y equation. Now, how can we solve for the time of flight? Which one of these equations could give us back that time?
The third one.
This equation right here is actually sufficient for us to get the total time of flight in both of these cases. The reasoning behind this is, what is the height when this thing is done moving? Where is this ball going?
To the ground.
It's just falling
0.
to the floor. So yeah, 0. We're asking the question, well, when the position of y is 0, how much time does that take? So 0 is going to be equal to 1/2 gt squared plus h. So if I take this and I solve for the time, t will be equal to the square root of negative 2gh. What do you think is the deal with that negative sign in there? Why would there be a negative inside of a square root? How is that okay?
Because it's going down.
Mathematically, this would give us that time was imaginary, but you can't do that. This is negative 2gh. What rationalizes this? Which way is...
Because gravity is negative.
Wonderful. Gravity must be negative, because by saying that the height is h above the ground, we are saying that, yo, upwards is positive, but gravity acts downwards. So by definition, since these arrows oppose, if I'm saying height is positive, gravity must be negative. Negative, negative gives us back a positive time. So this equation is all we need in order to know about the total time of flight. And heck, you could even figure out what the equation is of this parabola, because we know that that guy is going to move as a negative parabola, right? And the way that we would do that, the way that you could show that, is by solving these two parametric equations. So this is y as a function of time, but if instead I wanted to know, well, hey, what is y as a function of x, right? All we have to do is take this equation here and solve it for time. Let's go ahead and do that. So I have x2 is equal to v sub o multiplied by time. How do I get time alone?
Divide.
Divide by v sub o. So this will be x2 divided by v sub o is equal to time. Now, if I take this guy, my new definition of time, and I plug it in here, this will tell me what this equation is for the trajectory. So this is to say that y is going to be equal to 1/2 g t squared, but we just redefined t. So this will be g times x divided by the initial velocity squared plus h. And so y, and it's no longer y as a function of time. Now it's y as a function of what variable?
X.
Y as a function of x is going to be equal to 1/2 g x squared over v naught squared plus h. This is our parametric solution to what is the exact shape of this trajectory. This tells us not how does y change over time, how does y change as a function of x? Is this okay?
Yep.
And again, this is telling us, okay, y is going to be a parabola of x, but Marianne, how come this is a negative parabola?
Because the gravity is negative.
Perfect. Gravity here is actually negative, so this coefficient here is on the x squared. It's saying that that is a negative x squared. So let me go ahead and show you this in Desmos, just because I know there's a little bit of new data mixed in here about parametrics along with our review, but you know, this is my smart group, so I don't shy away from hitting you with the good stuff. What this is saying is that y as a function of time is going to be equal to 1/2 times gravity, which is negative 9.81, times x squared divided by, divided by, I need parentheses, v squared plus h. I'm going to add a slider for v and a slider for h. And so keep in mind that outside of this space, we're going to have non-real solutions. So to make sure that it's all real, we're just going to stay in quadrant 1, right? And so what do y'all know about projectiles? The faster the velocity is, what is that going to change about the range?
It's gonna get smaller.
The faster a velocity is, what does that change about the range? The faster a bullet is, does it go further or does it go shorter?
It goes
Further.
Okay.
The higher velocity is, the further it's going to travel before it hits the ground. And that's what this function does. The greater the velocity is, because of its position in the equation, it's saying that, hey, the trajectory, it's going to cover a larger distance before it smashes into the ground, before y gets to 0. And what about if we shoot it from a greater height? Will it travel further or less far?
Go less.
From a greater height?
It should go further too.
It should also go further. So if you fired a projectile from this height, it's just going to go and hit the ground. If you fire the same projectile from a greater height, because it has more time of flight, it will travel a greater distance before it smacks into the ground, which is also what this trajectory model does. If I lift it up, it allows our projectile to travel a greater distance before it gets down to y equals 0. Okay, so quick recap. Whenever you have perpendicular dimensions, any two directions which are 90 degrees to each other, they don't play. They do not affect each other. And because of that, you can set up their independent equations, well, independently, which is exactly what we did. We got one equation for y, because we know that there's gravity this way. We set up one equation for x, and there is no gravity this way. So equations in the direction with gravity, they get a gravity. Equations perpendicular to gravity don't get gravity. And if you take any two independent equations of motion that are functions of time, you can substitute them into each other, and that new equation will tell you what is the shape of the pathway, though in here, the time information has been removed. This is a lesson that we're going to use again when we get to ramps, because keep in mind, when it came to talking about ramps, in order to do anything interesting there mathematically, we had to take our forces on the ramp and break them up into two independent directions of motion. The block is going to go up and down, so I don't care about any direction that isn't either going in the direction of motion or perpendicular to it. So we take gravity, mg, and we split it up the same way we did in the warm-up. I'm not interested in mg. I'm interested in mg cosine theta, and I'm interested in mg sine theta, because these two components of the weight, they don't affect each other. They're perpendicular. And one of them is in the direction of motion, and one of them is perpendicular, which helps me figure out my normal force. My normal force has to be equal to mg cosine theta. Otherwise, the block will smash through the ramp or go flying into the sky. They got to be equal and opposite. Oh, I'm sorry, opposite. Let me put a negative on one of these. And any friction here is not going to oppose the weight. The friction is only going to oppose mg sine theta. This is another case where we are breaking up our forces and setting them up in such a way that we only have pieces that are parallel and pieces that are perpendicular, because it makes it easy to see what is allowed to interact with what and what is independent of what. So for tonight, I'm going to post one video that I want you to watch, and again, give me a 250-word summary of it. Just outline the main points in the video in your own words. That's all the homework for tonight. Tonight, I'm going to look at your guys' submissions for that most recent free response that I gave you, and then tomorrow in class, we'll start by going over it together so that we can talk about what's worth how many points and look at some good versions of solutions. We'll talk about strategies of how to maximize your point totals. And then we will continue our review. Tomorrow, if there's time after we do that free response, I want to talk about Newton's laws. Are there any questions?
Mm,
Is this all okay so far?
Yeah.
Okay.
Yes.
And if you want to go above and beyond in terms of stuff that you could do on your own, clean up your lab notebook. Like I said, finish the table of contents, number out the rest of the pages, and start reading over some of the labs that we did at the start of the year, especially the one about the ticker tape and how we measured gravity the first time, just because questions about those labs can legitimately appear on the test. Y'all have a nice day, and I'll see you
Mr.
tomorrow.
Robinson,
Yes?
is that free response assignment still up?
Yeah, I didn't set a deadline. I just left it open. So if you haven't done it yet, get it done.
Okay, thanks.
And
Bye.
yeah, if you have any issues, email me. Take it easy, y'all.
thank
All right,
you.
thanks. Bye.
Thank you.
Bye.
Yeetus.